So I'm going to talk about this search for this new planet, which, as you heard, might replace the previous Planet 9, which was not really Pluto. It was never really a planet. This was this idea suggested to me by my daughter when she was 10. She was like, Dad, do you want to know how to get everyone to stop hating you? I'm like, first, right, I disagree with the premise of your question. Second, yes, please tell me. And she's like, you find a nuke and you name Pluto. And I laughed. And then shockingly, years later, we were looking for planets. So there's at least one share here if anybody who's here. And one share right here, we sound like an the height. If anybody cares. I don't know if anybody cares. Okay, so if you're going to talk about finding new planets in the solar system, it's best, I think, to go back to the last time there were no new planets. And the last time there were no new planets would be something like 1780. If it were 1780, and if it were 1780, and right now, you could go up, look in the sky, and you could see all the planets. You could see Mercury, if you knew where to look. Most people had seen Mercury by then, probably. How many people have seen Mercury? Good. Astronomy department. Who has not seen Mercury? Theorists. Okay. So you can see Mercury. You can see Venus. Something like go out tonight. Venus is a little hard to miss. You can see Earth right there for you theorists. Mars, easy to see tonight. Mars is like almost straight overhead. Beautiful. Jupiter's up there tonight. Saturn's up there tonight. And that's it. 1780. That's the last planets those were the planets that people knew about. And if you go back, I tried this. I'm not a real historian, but I went back and tried to find anyone who had written about speculating about new planets beyond the orbit of Saturn before the next planet was discovered. And I couldn't find anything. I actually don't think that people really have the idea that there might be new planets out there. Galileo had used his telescope to realize that there are stars that you couldn't see, that there are moons around things like Jupiter that you couldn't see, there are rings you couldn't see. But the idea that there might be planets that are unseen, I couldn't find. It doesn't mean that nobody had thought about it, but I couldn't find it. So it took an accident, a very careful accident, William Herschel, who built the best optical telescope at the time, and he was using it to map out the sky. He would, look through his big telescope, which had the barrel as big as a house, and put down here star, and he'd write them all down. And when he got to what turned out to be Uranus, it was fuzzy. He had the first telescope that probably had like arc second-ish resolution. Everything before that probably was like a 5 arc second smear or something. And a planet like Uranus would just look like any other star. He recognized it as something weird. Weird is okay. Even then, people knew, they didn't know what they were, but there were planetary nebulae, there were galaxies, all these things were known fuzzy objects in the sky. So he assumed it was just one of those. He came back the next day and he was careful. He came back the next day, star. And that fuzzy thing went from here to here. As soon as you see the fuzzy thing go from here to here, you realize it's not a star, it's not a galaxy, even if you didn't know what a galaxy was at the time. It's something in our solar system. It's something that's moving against the background stars. He was very excited, kept on tracking it. Herschel did not think that it was a planet. So a couple of people jumped up and down like, you just found a new planet. And he was very reluctant to call it that for a while. He thought probably comets. People knew about fuzzy comets in the sky. And I think they even knew about comets whose orbits went beyond the orbit of Saturn. It was moving very slowly. So it was clear that it was beyond the orbit of Saturn when it was found. People knew about those. And so he thought, yeah, maybe it's a comet. I'm not quite sure what it is. At the time, the idea was, well, you need to find its orbit. It's either going to have a cometary orbit like this, or it's going to have a planetary orbit, go on a circle around the sun. And it had already been observed for a little bit, so nobody quite knew what to call it. Herschel eventually, even before the orbit was known, Herschel eventually got convinced to call it a planet and decided to name it George. Didn't stick, but it was the original name, George. George named after King George. Who didn't like King George as the name of a planet? Who liked it the least? Americans did not care in 1780 so much. It's the French. The French were like, no. So that didn't stick. And eventually it got to be Uranus as we know and sort of love and make fun of. But when the orbit was still not well known because it had only been observed for a little bit of the time. So it was tracked. And it really, the final understanding of what its orbit was came from Alexis Bouvard. Alexis Bouvard has more titles than me. I'm kind of jealous. But he also wrote this very exciting book, Tables of Jupiter, Saturn, and Uranus. And in these tables of Jupiter, Saturn, and Uranus, he figured out where Jupiter and Saturn were supposed to be based on their mutual gravitational perturbations, not just, an ellipse, but the perturbations during the ellipse. And then he figured out where Uranus should also be. And it's not, a little bit of math, but it's this kind of stuff that we all kind of, I think this is your homework problem. Somebody said you're working on planet homework problem. Mm-hmm. I think this is there. Perturbations of Jupiter and Saturn. And then this is the theory for where Uranus should be. And he did something really interesting, which is if you go to the discovery of Uranus, 1781, and you can see every date he has after that, people observed it. And this other column is I'll zoom in over here, actually, if I can do that. This other column is the discrepancy between his theory and where it was observed at the time. So it's good, not great. But the really cool thing is he went backwards in time. It was discovered in 1781. It was observed by somebody else cataloging the stars in 1771, who cataloged it as a star, but that didn't go back the second night to look. The telescope wasn't as good. It wasn't identified as a fuzzy objects naval attack. And then he found that, then he realized, it was also cataloged and all the way back to 1690 was the first time Uranus was cataloged. It was Flamsteed, famous for people who observe stars. Flamsteed observed it in 1690 and it was in Taurus. It was the 22nd star in Taurus at the time. It's 22 Tauri. If you go look at your stars in Taurus, there's a 20, there's a 21, there's a 23, there's a 24. There is no 22 Tauri because that's actually Uranus. So alternative name if you get tired of hearing Uranus all the time. But the other interesting thing is, so he could go back. That's pretty cool. Go back all this time. Going back all that time gave you enough arc that you could see it's really in a circular orbit around the sun. This is planet doing things planets should do. And it was the only thing it wasn't quite doing. It didn't quite fit the theory perfectly. Bouvard was what we would call today the preeminent astrophysicist of his time. You all know those people. They're all the same. They say, my theory is perfect. The observations are wrong. Do better observations. You know those people, right? Constantine, you know, right? So theory's perfect. And so astronomers are like, okay, I'll go back and do better observations. And so starting in about 1819, they really started observing Uranus very carefully to make sure that their observations were not messed up. And from 1819 to about 1840, observations kept coming in and it was not in the right place. And Bouvard, he's good enough to know that he needs to have a little bit of wiggle room. And he says down here, there's an alternative theory, probably not true, but there's an alternative that maybe there's something else out there tugging along at Uranus. By 1840, this was amongst the astronomical community. I think, as far as I can tell, again, trying to read old books and articles and understand how people were thinking, which is not always easy. By 1840, it was widely accepted that there was another planet beyond Uranus. I say this because in some sense, I feel like we're in 1840 right now. It's not widely accepted, may not quite be true, but all the evidence was in at 1840 that there was another planet, and people understood that there was another planet and that it needed to be found. It's just that nobody knew how to find it. And so until 1845, Urbain Verrier sat down, did some calculations using these data, literally these data. He was at the same observatory there in Paris, using these data to try to figure out where this perturber was. He made some very questionable assumptions, including believing that he knew the semi-major axis, which was wrong, and a couple of other things. All of his assumptions turned out to sort of cancel, and he came up with a prediction of where this should be. He sent it to the observatory in Berlin. They opened up the telescope, and that very first night, they found what we now call Neptune, which is, to me, I mean, this remains one of the most amazing stories of kind of discovery and prediction, and there it is. And there was a lot of luck involved, and if it had been 50 years early or 50 years later, his calculations were actually wrong, and he wouldn't have found it and not gotten quite so famous, but worked out for him. He's not complaining. Okay, let's go back here. And at this point, people got very excited about the idea of new planets compared to 1780, where no one thought about new planets. Suddenly, you could find a planet, as it was called for Leverrier. He was the astronomer who found a planet at the tip of his pencil. And he got very famous. His statue is still in Paris, right at the observatory, staring up straight at Luxembourg Gardens. Very pretty spot to have your statue. Trying to reserve a spot in that set. So very small spot. His name is inscribed in the Eiffel Tower, one of 50 people whose names are supposed to be there. A lot more there these days. People were like, I want to get famous too. And they started predicting planets left and right and left and right. And we counted recently, and there's something like 34-ish individual predictions of planets, additional planets in our solar system based on some sort of observation. And of those 34, they've all been wrong. And of those 34, most of them have been wrong and kind of embarrassingly wrong. So the most unembarrassing, but which should have been embarrassing, but turned out to be unembarrassing one is the story everybody knows. And that's the discovery of Pluto. Of course, Pluto was found when it was expected to be planet X, which was more massive than Jupiter. But it turns out, Pluto, as we know, is just this tiny little thing in this crazy orbit that goes out beyond the orbit of Neptune, dips inside the orbit of Neptune. It was thought to be huge at the time it was discovered, only because people were looking for something huge, because they thought there were perturbations still left to explain of Uranus and Neptune. There aren't. Uranus and Neptune are exactly where they're supposed to be, but it turns out there were actual bad data. Leverrier was Bouvard was not entirely wrong about the astronomers having some bad data in there, I'm embarrassed to say. But the exciting thing happened, I would say, for understanding what's going on in the outer part of the solar system starting in 1992 with the discovery of the Kuiper Belt, the next new objects beyond Pluto in the Kuiper Belt. And as of now, they're probably, I used to know the numbers, and now there's 4,000, 5,000, I don't even know how many objects are known beyond the orbit of Pluto, Neptune. And they all have orbits in the class of with Pluto. Pluto is weird because it was tilted. Pluto is weird because it was eccentric. If you look at these things, many of them are on eccentric orbits. Many of them go inside the orbit of Neptune. Many of them are inclined. It was very clear back in the early 2000s, as these were being discovered, that Pluto is not part of this system of regular planets. It really is part of this Kuiper Belt. The nice thing is, this Kuiper Belt at the edge of the solar system gave us another way that we could start to gravitationally probe whether there still were any other planets left to discover. And by about 2002, everything that we saw in the solar system, you could explain with what we knew about the solar system. There was absolutely nothing that required something new. 2002, we ruined it. I apologize. And that's what this discovery, this big survey that we started in the early 2000s, done right up the road here at Palomar with the 48-inch Schmidt at Palomar, with the first time we put digital cameras on it and roboticized it and really get a big survey of the outer solar system. And one of the, I think, most exciting things that we found by doing this was this object, Sedna. Sedna is on a 5,000-year orbit around the sun. It goes out to something like 500 days. You look here, and it's the really interesting and weird thing about Sedna is it never gets close to any of the planets. Neptune is right here, and it's on this orbit. If you think about what we know or think we know about planet formation, things form in circular orbit. So let's stipulate that Sedna formed in a circular orbit. How could it get to this orbit? Well, if this orbit were down here, closer to Neptune, it could just be scattered. You scatter from Neptune, you come back to the point where you were scattered, and you stay like that. But it's out here. It never comes close to Neptune. How did it get on the circular orbit? At the time, we were trying to figure out what might have happened, and the answer is, could be something like this. I'm going to give you a very toy model of here's the sun, here's Neptune now, and I'm going to put an object in a circular orbit at Neptune. What happens? It eventually encounters Neptune. When it encounters Neptune, it gets a gravitational kick. That gravitational kick can either put it on an eccentric orbit that goes beyond Neptune or an eccentric orbit that goes inside of Neptune. I'm going to only show the beyond Neptune versions of it, but you get a kick like this. You always come back to where your kick was. It's an impulse. As soon as you get this impulse, you're still on a closed orbit. You have to come back to the same spot. You can diffuse around and do weird things because there's more than one planet, but we're going to just do this. Okay, so you go like that, you come back. What happens? Bad news, if you do this enough times, you're going to find Neptune again. Just, maybe not the first time, maybe not the 10th time, maybe not the first million years, but you'll find Neptune again, you get scattered again. Bad news, happens again, and if you keep going out, you are bound less and less strongly to the solar system. It's a random walk. You could go in, you could go out, but every time you go out, you're bound less and less strongly to the solar system. It's a random walk down like a slippery slope, and that slippery slope has a cliff on one end. So it's like, I explain this to undergrads. It's not as big a problem at Caltech because it never snows. But if it does snow, don't go climbing on a roof and drinking and start walking along the icy roof, because you'll eventually fall off the roof. This is, I think, a statement of fact. If you're drinking and you're walking on an icy roof, you will fall. And this is why. Sort of. Random walk. Okay, so this didn't help. This doesn't make sense. How do we make Sedna? The way to make Sedna, there's only one, not only one, but let's say one obvious way to make Sedna is when you're out here somewhere, get an impulse out here. What's going to give you an impulse out here? Well, you could just say there's a planet out there, but everybody knows there's no planets out there, so that's crazy. So instead, you invoke a passing star. Passing star comes by out here and gets some sort of impulse out here. Your orbit is now, your perihelion is raised, and now you're safe. You can stay in this orbit until the end of time. Nothing, unless it's not a passing star, will ever change your orbit. We were really excited when Sedna was first found back there in 2003, because it seemed like a fossil record left over from the early part of the solar system, the formation of the sun itself. When would there have been passing stars? When the sun formed a cluster. This is a signature of the cluster formation. It's not true. We thought it was true, so I'm just going to remind you right now, this is not true. But it's a cool idea, and we were excited about this. And so we spent a good decade looking for more things like Sedna in hope to try to read this fossil record of what was going on. Had an entire PhD lifetime of looking for these. Never found one. I apologize to her ahead of time or behind her, doesn't, but she just has a nice job. Doesn't matter. But we never found another thing like Sedna, but we found some other weird objects along the way. We and other astronomers who were looking for these sorts of things found some other, not always Sedna-like with the raised perihelion, but just really eccentric objects along the way. And here's a collection of the ones that's got us wondering about this. When I say us, it's always going to be me and Constantine Keating, and we sort of worked, I would say hand in hand or fist in fist or punched a one day. But we worked together pretty strongly on this, and we found these objects. Sedna is a special color that I can't tell from here. You can tell one of these is that it must be this one. It's kind of far perihelion. But some of these have, this is Neptune again. Some of these are not that far from Neptune. They're all kind of far from Neptune, still too far when they should be. But the weird thing about these, as you might know, is they all go that way. And any good astronomer will be like, yeah, sure, whatever. Statistically, that doesn't seem like that big a deal. It actually, with this number of objects, and it's only 1, 2, 3, 4, 5, 6, 7, 6 or 7, that's actually a statistically big deal. It's about a 1% chance that you would have them all pointing in that direction that strongly, even taking into account the very crude way we dealt with observational bias in the time, which was we just looked for other objects that were less eccentric and they were pretty uniform around there, did the calculations, about 1%. You know, that's not 3 sigma, but 3 sigma is just a made up number that doesn't mean anything. So I like 1%. 1% is pretty good. And so we sat down and tried to figure out what was going on. It was pretty clear there's something weird happening. You could explain a planet, but everybody knows there's not a planet out there, so that's dumb. And we didn't want to be dumb. So we spent like a year trying to figure out what plausibly could cause this alignment. We looked at self-gravity. We looked at some weird instabilities that might happen. We re-looked at observational bias way too many times, and we failed. We were so disappointed in ourselves. Like, we could not come up with a good explanation. So we finally, like a year in, we were like, God, are we gonna think about, well, maybe it's a planet, it's so embarrassing. But might be a planet. So you could just write down some pretty simple equations. These are just pretty simple. This is just a Hamiltonian for an object that's on an eccentric orbit around the sun under the influence of a central set of planets. So there's a J2 central set of planets and one external perturber on an eccentric orbit. Not all that complicated. I couldn't do any of this, but this is constant. But like a good talk. And you can see things that matter, like the difference in this curly pie, which is the difference in where they're pointing. So it's got some orientation in through there. Got some terms that deal with eccentricity and mass of this planet. And so you could write down these equations and make some predictions, and it actually kind of worked. Embarrassing, it kind of works. And so we were like, this is it really works well, and it actually predicts that if you have at least I'm not going to start yet, right? Yeah, you'll see this in a minute. Here's Neptune. There's going to be a planet here. I'm going to show you some n-body simulation stuff. Here's the planet. What the theory, the secular theory, you make some assumptions when you do the secular theory. One of them is that the orbits don't intersect, because that kind of blows up your secular down here. And we also assume that intersecting with a giant planet is bad news and you're going to get ejected pretty quickly. So this theory predicted mostly a set of objects that kind of get nestled inside here. They're kind of hugged by the giant planet Ma. They lightly oscillate around. They're not super. Not like they're really stuck right there. They just spend more time right there. So we're like, cool, let's at least, before we jump up and down and say it must be a planet, let's do some simulations, see what's going on. And the answer is you do this and you watch what happens. The planet stays here, the orbit of the planet. Each of these blue things is a test particle that we start on a very eccentric orbit. And the first thing that happens is you notice that it ejects a ton of stuff. Crossing the orbit is a giant planet, bad news. Second thing that happens is inside here, you really just have objects precessing, not much of an effect for the inner things. This is why only the really eccentric things we were noticing. The inner things just precess like this. And then you'll start to see these very eccentric things start to get caught over here, just exactly like we predicted, like that. Nope. They're coming. I promise you they're coming. This one gets stuck forever. No, so now, not to get stuck. Not a single thing in our very limited simulation here gets stuck on this side. They do the dynamics that the secular dynamics said, but then they cross the orbit and they get ejected, which was not taken into account in the theory. So we're like, oh man, this is weird. What's going on? What's going on is they're all over here. Why are they all over here? This is not what we expected to see until we saw it. Then we're like, oh, duh. Of course they're going to be all over here. The answer is it's not that there's anything particularly clever going on. It really is just that, you're on orbit, you go faster here, you go slow out here. Same thing happens here, faster here, slow out here. You spend most of your time out here, most of your time out here. Spending your time as far as possible from a giant planet is smart. Stay far from giant planets. The bad news. Coming in close, if you're going to have to cross the orbit fast. So you cross the orbit fast. The planet itself is crossing the orbit fast. It's not that these are in a cluster that's going to be stable forever. These are just the last remnants of the things that will eventually come back in a billion years. These guys are all gone too. They're just the last. And remember how many started that way? There were so many objects at first. This is just the tiny vital remnants out here. And so if you see a cluster that looks like this, you really have a planet that looks like this. And one of the things I didn't show you, but it's fun to see, is that these objects in the cluster are all on average tilted by about 15 degrees compared to the plane of the solar system. And as I'll show you, that really gives us a good clue on what the orbit of this planet has to be. So Constantine and I were very excited. We're like, okay, do we want to write a paper being the 35th and 36th people saying there's a planet and they're eventually being wrong and stupid? We were like, yeah, no, we didn't. We were like, okay, we would like to make a prediction and have that come true before just jumping up and down and saying there's a planet. So, here the obvious prediction, well, there'll be more objects found over here. That's true. And I'll show you later, it's turned out to be true, but it's taken nearly a decade to find enough more to show that that's not true. So we're not patient people. We want something you could do right away. One of the really interesting things is that in addition to this planet, in addition to making this cluster, it does some other weird dynamics that we, Constantine, understand now, which is that it takes, if here's the solar system, here's these objects off in this direction, it takes these orbits, when they become unstable, as they're leaving it, one thing they do is they twist by about 90 degrees, either this way or this way. And when they do, they also twist their inclination by about 90 degrees. So now they're plunging into the plane of the solar system, or over here during plunging into the plane of the solar system. Very weird, nearly 90-degree inclination to the solar system, things that we don't have in our solar system. So this disturbed me greatly. Our theory predicts these things. They don't exist. We should sue them. We're wrong. So let's figure out what's going on. And what was going on is I was wrong. We do have these things in our solar system, and I'd forgotten about them. I'd forgotten about them because everybody forgot about them because nobody had any idea where they came from, so everybody ignored them. Occasionally they would get discovered, and the leading theory for these weird high inclination things in the solar system was that there must be, for no reason whatsoever, a belt of material perpendicular to the plane of the solar system out at a few hundred AU. Okay, maybe. And then everybody forgot about them. So I realized that they existed, went and collected all the data on all of them. And I'm going to show you a crappy looking plot, but I love this crappy looking plot because it's literally the plot that Constantine and I stared at my computer to decide if this was true. It's a plot of the spaghetti plot, we call it, not a plot. So this is a plot on this axis is perihelion longitude. It's the direction that orbit is pointing. So 360 degrees of a clock. And inclination, just inclination. Each of these little pathways that you see is the dynamical evolution of one of these objects over a period of time when it would be observable. So that means that it has to have a perihelion that comes down close enough that we could observe it. So what do you see? This pile of spaghetti is our cluster. It's all at a certain perihelion longitude, which is where we observe it. And it has inclinations up to 45 degrees. This is about right. And they wander around here through this portion. Remember how I told you that they get lost sometimes? This is their lost pathway. They get slightly elevated in inclination, and then they twist by 90 degrees. They come up here. They can come back around and come over here. These are these wings. So it's 90-degree-ish inclinations, and they are 90-ish degrees from the cluster. Does that make sense mostly? Okay. So we literally did not know what this plot was going to show. We had this plot, and I'm like, okay, here we go. And there they are. These are the objects we knew ahead of time. 1, 2, 3, 4, 5, 6. And it's not huge numbers, but it's 1, 2, 3. There's 2 of them over here. 4, 5. And to us, staring at that the first time, our jaws hit the floor. I mean, this was literally to me the moment when it went from, isn't this a fun little story that we're telling? Ha ha, it might even be true, to, oh, there's a planet out there. Holy crap, we have to do something about this. So this is when we finally wrote that paper that then became the big story of Planet 9. I wanted to show you what these objects look like because they're cool. These are the objects we already knew about. There's Planet 9, and these are the ones that are on these, I like to call them the wings, these perpendicular wings to the solar system. And they're exactly where they should be for some sort of eccentric perturber doing exactly this. And these are ones that are on their way out the door. So super exciting, super cool. We wrote this paper, and it seems a little bit crazy to say that 34 astronomers were wrong before us, but you should believe us because we're right. But in our defense, 34 astronomers were wrong before us, and you should believe us because we're right. So I think we're right. And since that time, we have if we're not right, we want to be the ones who prove ourselves not right. You don't want some, snot-nosed grad student coming in and showing that we screwed up. We like to be those snot-nosed grad students ourselves. And so we have kept on trying to come up with new and better tests for if Planet 9 is real, and if it is real, how do we learn about where it is, and how do we predict it, and then eventually, how do we find it? So first prediction, obviously, was there will be more objects found on this side of the cluster. Interestingly enough, the statistics are good, but not great. If you find enough objects, there better be some on this side too, or then something even weirder is going on that I don't understand. So we actually now in the past, in the past 8 years, since we've been talking about this, the numbers aren't huge. It's hard to find these objects, but here's all the new ones. There's one over here and all these over here. Looks pretty good. This was what we predicted. Looks pretty good. I'm pretty happy about that. Still not particularly worried about observational bias, because every time we do find new objects, we get a even better handle on how the observational bias works, and is great. So now we're just for the statistics of the clustering, we are at something like 0.2%, something like that. So here's another. One thing I didn't tell you of the fun things that Planet 9 does. And you'll see it here. One of the things that Planet 9 does is it takes an object's perihelion, one of these eccentric objects, it takes its perihelion and it modulates it. Goes up, goes down, goes up, goes down. And it makes things like Sedna. That high perihelion of Sedna is a direct consequence of Planet 9. This was fun because it was not even something that was in our brains we were thinking about. We were not trying to explain perihelion of Sedna. We were just looking to see what Planet 9 would do, and it naturally fell out that it would raise these perihelia just like we expected to do. But it does another really cool thing. As it's raising and lowering perihelia, this is going to be Planet 9, little solar system inside there, a test particle, and this is one that's now not stable. So it raises and lowers the stable ones, but it does this to the unstable ones. When you get your perihelion down too close to Neptune, you suddenly get attached to Neptune, and your dynamics lose Planet 9 because Neptune is a much bigger influence, and you can wag around all over the place and change your orbit. Then your perihelion will go back up again, and then you're just being affected by Planet 9, and you go back down again, and then we go crazy. Interesting things happen. It's the same process that I talked about before, where when you get close to Neptune, your orbit can go out, but it also goes in. So we're going to see a case where eventually a particle gets scattered inward. So the stable area is over here. This object never really makes it in the stable area. Notice every time it comes down, it swings around, go up, swing around. I don't know how long it takes this one to do it. And when it swings around, the semi-major axis will change, kind of hangs off for a while, gets too close. Eventually, it's going to hit a period just by chance where it swings down to Neptune, and Neptune pulls it in. It just changes the semi-major axis. The random walk happens to go the right direction, and it gets stuck. But it gets stuck in the inner part of the solar system. And this is no longer one of those really distant eccentric objects. This is a perpendicular, we can call these centaurs now. It's in the giant planet region, and it actually has a semi-major axis in between Jupiter and Neptune. And again, we knew about these objects ahead of time, and nobody had an explanation for them except that this, again, 200 weird AU thing. So interestingly enough, if you do enough of these objects, you can predict where they're going to be. And this is not something I would have thought about ahead of time. But the regions that are populated by objects coming from Planet 9, this is the normal solar system. We understand every single point down here. Every one of these points is a real object, and it has semi-major axis versus inclination. Same objects over here. Perihelion versus inclination. I like perihelion because Neptune is here at 30, Uranus at 20, Saturn here at 10. The density of the green region is where we expect Planet 9 to put objects through this process that I just showed you. And then there's these real objects. And it's here, down into here, not here, up here. And these are the same objects, but not here, up here. So the fact that this one's here means that it had to have a 10 AU perihelion, and it just fits. I mean, it's hard to figure out exactly how to do the statistics on this, because understanding the observational biases on this particular set of objects is much more difficult than understanding the stuff before. Nonetheless, this to me just kind of blew my mind when we saw this. We're like, okay, that's cool, right? Yeah. Cool. Yeah. Okay. All right. Okay. Good. All right. So there's one more. Good. My time's out. My favorite test that we just did about a year ago. We came up with this like a year ago. And it's really, it seems mundane, and yet it's incredibly powerful. Here's the mundane test. Again, one of those things that's really important is those perihelia being modulated by Planet 9. So they come down to the orbit of Neptune. Maybe they interact with Neptune, bad things happen. They go back up, they go down. Even if we pass Neptune, all sorts of things happen. If no Planet 9 exists, then you still have objects out there in the outer part of the solar system, and they have these eccentric orbits, and occasionally they diffuse. They diffuse because if there were just the sun and Neptune and a Kuiper belt object, no diffusion happened. But you have enough planets out there that weird dynamics happen. They diffuse, and so maybe they diffuse inward, and they get too close to Neptune, and they have an encounter with Neptune. What's going to happen? They're going to get scattered outward. Maybe they get scattered inward. What's not going to happen, most likely, is their orbit the perihelion is not going to keep going to lower distances, because there's nothing to do that. There's a barrier. Neptune is a barrier. Hard to cross that barrier. And then once you cross that barrier, there's no reason that you don't just diffuse back again. And so it's a really tough barrier. It's not impossible. Things will diffuse across Neptune. We'll see them, but it's rare. You shouldn't see too much of that. In contrast, if Planet 9 exists, it's pushing. You get to the Neptune barrier, you might still get ejected at the Neptune barrier, but if you make it through, you're pushed. And so you have a much better chance of surviving and of being pushed. So here are the observations. Here's two sets of simulations. This is with Planet 9, without Planet 9. This is perihelion distance, and I'll remind you again, this is Neptune is at the very top at 30. There's a Uranus, Saturn here. And here's the no Planet 9. And this is semi-major axis. So I'll apparently cut this off down here. Semi-major axis. If you have Planet 9, the prediction is that you will have all of these objects pushed inward all the way past even Uranus's orbit and almost into Saturn. Saturn, hard to get past Saturn. Saturn, big bully. And so not much happened there. If there's no Planet 9, you get a few things, but they really just don't push very far down. So this one, super clean, super clear test, super biased. It is really hard to say, okay, we can set, if I just showed you the real data, you would say, oh yeah, look at that. There are a lot of objects in through here. But it's easy to find those objects. We find them at perihelion. Now, reflective sunlight objects like we're looking for, they get fainter as 1 over r to the 4th. It is really so much easier to find something at 15 than even at 30, where it's 8 times fainter. It's a good couple magnitudes, 3 magnitudes fainter, and you're not going to find the same surveys. So what do you do? So we came up with, I'm super geekily excited about this unbiasing we did, so much so that I made my wife sit down and listen to it one day and explain to her idea. So that's very exciting, but it's super cool, where you basically turn every detection of an object if you detect an object inside of 30 a year, once you detect the object, you don't know what its orbit is when you find it. And there's no is not the right word, but there's a very easily quantifiable bias on what its orbit is going to be when you find it. And it's a probe of all of the distribution of the orbit's interior. If this were the distribution and I found an object right here, then the probability would be that it's perihelion. And if I found an object at a distance, now the discovery distance, not perihelion, not some no direction. If I discover it right here, well, there's no objects back here, so I better be finding it right at perihelion. In contrast, if I discover it right here, there's a pretty good chance that I can find these things in through here. So it is a very powerful and absolutely undisputable debiasing method. Anything else you're debiasing, you can argue about this and that. Maybe this one can't argue. Anyone want to argue? You can't. Sorry, don't. You can't do it. There's no way to do it. And the answer, which we didn't know because we just had the data, and then we figured out this method for debiasing, and sat down and ran it and pressed the button. And I didn't know. I didn't know what it's going to be. I'm like, I was kind of nervous. And the answer is that this test is preferred this simulation is preferred at something like 5 sigma. You cannot. This can't be this. You cannot have. You can't have a solar system that doesn't have something pushing you past the Neptune barrier. And to my knowledge, nobody has come up with any idea for anything else that could possibly cause that effect. It's funny because that the clustering is the visually obvious effect and aesthetically pleasing. This is less so, but I think this is the more slam dunk case that there's a planet out there. And if there's not a planet out there, then you need separate explanations for the clustering, for those weird objects that are like that, for Sedna, for all these other things. So, maybe there's an explanation for all these other things, but I don't think it's going to happen until there's a good explanation for the rest of these. I think Planet 9 is really the only thing we got going on. So what do we know about Planet 9? Well, one is, how do we find out anything? The real way we've tried to figure out how big it is, what it orbit is, stuff like that, is we take those computer simulations like you saw and just adjust knobs, make it a little more massive, less massive, tilt it this way, tilt it that way, change its semi-major axis, change its eccentricity, and see how it affects things. And there are some really strong effects that allow us to read the record that we have and see what we get. And those effects look something like, here's just a random bit of them. So all these plots are going to be in semi-major axis out here, and these are all objects that have perihelia inside of about 80 AU, so they can be observed. And this is the longitude of perihelion, the direction that the long point of the orbit points. So this is 360 degrees. This is the cluster, and you see this cluster, and these are normalized by the number at every semi-major axis. So where you see just a generic red color here, that's because there's no preference for semi-major axis. Inside of a certain distance, you saw that in the simulations, right? You saw those green objects on the inside just precessing, going in circles. That means there's no preference for semi-major axis. Outside of a certain distance, you have a preference. There are many more objects here than there are here. And here, 180 degrees was the delta curly pie, which means it's 180 degrees from where Planet 9 is. So that's that oppositely situated cluster. A couple things are interesting. One is there's always this wall, as we like to call it. This wall is a function of the mass and the semi-major axis and the eccentricity. It's basically a function of mass and perihelion distance. So move the perihelion in, the wall moves in, increase the mass, the wall gets bigger. So you can use that as an adjustment. There's the width here is a really important one. These simulations are all the same semi-major axis nearly, and they just increase the mass from 4 Earth masses, 5, 7, and 12 Earth masses. And what you'll notice is that width decreases as you get to higher mass. Higher mass, if the process is getting rid of material over time, the higher mass object gets rid of more of it, and the only stuff that lives till now is that stuff that's really very anti-aligned. Whereas if you're only 4 Earth masses, that's nearly 180 degree cluster. So the other thing, do I have the next plot? No, I don't have that plot. You can do the same thing with inclination and show how inclination shows things. With all of that, we can then start to put together a best model fit for what's going on. Here's our best model fit and the real data. This is when we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 points. I think those are the 11 points I just showed you. This is a fun plot because each of these blue lines is the observational bias. You can see the observational bias at the same time. The probability that you would find an object at that semi-major axis if these objects were uniformly distributed across the sky based on where surveys have occurred. And notice there's a huge bias. This is what people keep saying. Oh, but there's huge biases in the surveys. Like, yeah, there's a huge bias down here. This is where the huge bias is. We should be finding all these things up here. You know where there's not a huge bias? Up here, where we actually keep finding these things. And you can then, again, do those calculations and show what the probability is. This is the best fit distribution. It's very broad. It's got a wall at about 200-ish AU. And as you'll see, it's a moderately low mass Planet 9. So we can use all these simulations. I'm not going to go through all of this. We use all these sort of simulations and we make a big emulator and we do big MCMC stuff and we figure out likelihoods and having probability distributions and blah, blah, blah. And you can see things that are interesting. These are each of the colors is a different mass from 4 to 20 Earth masses. You can see it in perihelion peaks around 200 AU with a pretty big tail. Inclination is a nice one. It peaks pretty nicely around 15 degrees inclination. A prime is something that I made up. It's about semi-major axis and it peaks nicely at a particular spot, which turns out to be at 400, 500 AU, but it depends on the perihelion also too. The point of these plots is really just to show that we did the math. And, we did the math, okay? That we did the math and we think we know. We had reasons for thinking what we know. And you could also see the highest ones are always blue. Blue is like 6 Earth masses. 6 Earth masses is the highest likelihood, but there's a distribution. So we have a full distribution of where we think objects might be. Okay, so 6 Earth masses. What is a 6 Earth mass planet at 500 AU light? Anybody know? 3 times? I don't know. What's a 6 Earth mass planet at 0.1 of you like? What's your favorite? If I told you I had a 6 Earth mass planet inside the over Mercury, what would you tell me it probably was? This answer has changed in the last 8 years that I've been asking this question. Yeah. I mean, I don't know. Yeah. So what is a 6 Earth mass planet? I don't know. At this distance, I mean, it could be. I don't think rocky is very likely. Icy. I think of it like super Ganymede would be the description. People like to call it super Pluto, but in Pluto, so I should get Ganymede instead. And Ganymede's bigger than Pluto by a good bit. We could call it super Eris. Eris is more massive than Pluto by good bits. Well, super Eris, but then it sounds a little fishy. Super Ganymede is pretty good. Super Ganymede versus maybe mini Neptune is probably the right choice. My guess, and it's just a guess at this point, we don't know. We know the mass, but we don't know what it is. It could be, there's some people who say, oh, maybe it's a black hole. And the answer is, yeah, sure. Like it's 6 Earth masses. It also might be a burrito. I mean, I don't know. But I think the most likely thing is a mini Neptune because I have a preferred formation mechanism, which is that it formed as a core in the Uranus-Neptune region. It's 6 or 7 Earth masses. That's a pretty nice core size to form there. It got ejected before it could collect very much gas around it, and it's been sitting out there. Might be true, might not be true, but let's assume that it's kind of super Neptune or mini Neptune-ish. What's it like? Well, here's my favorite thought of what the sizes of the planets really are, which no one ever seems to look at. You always get your kids' lunchbox version of it, where they're all about the same size. They're not about the same size, ladies and gentlemen. Jupiter's huge. Saturn, Uranus, Neptune, Kuiper Belt. One of these is Pluto. I think that's Pluto. Eris, much cooler than Pluto. Haumea. But that's the Kuiper Belt. I mean, it's pretty, looking at this plot, I sometimes just show people this and be like, Pluto's a planet? Really? Okay. Planet 9, though, if you put Planet 9 on there, it's big. This is not like, let's argue about whether it's a planet or not because it's an inch bigger than Pluto. This is the 5th largest planet of our solar system. This is, if it's a mini Neptune version, if it's a super Ganymede, it's a little smaller, but not really that much smaller. It's a big sucker out there. Okay. How are we going to find this big sucker? Well, apparently we're not yet. When we first wrote the paper, we had a bunch of press, and I would always confidently say we will find it within 2 years. I've said that every year for the past 7 years. This time I think I'm right, but I thought I was right every other time too. So you can ignore me, but I'm right. Here's where we think it is. So we know its orbital parameters pretty well. We can predict its orbital parameters pretty well, and that gives us a swath of the sky. So here's the ecliptic plane. Oh, no, here, ecliptic is that. This line here, here's the celestial equator. It's tilted by about 15 degrees to the ecliptic. You saw that in the original objects. Here's a probability distribution. The probability distribution peaks, like here's the galactic plane for us here. Probability distribution peaks in the galactic plane. Not happy about that, really. But the only reason it peaks anywhere is because it's on an eccentric orbit, and this is just based on how long it spends at the eccentric orbit. We have not figured out any way to directly figure out the mean anomaly, where it is in its orbit. And this is why your failures compared to our hero, Urbain Le Verrier, who knew exactly, I mean, he said, go look, the arrows there. We can't do that. We can say, oh, look, it's around here somewhere. Go look in all these places. And so we're failures, and our statues will never be in Paris. And I'm sad, but that's okay. So here's the orbit. But more interesting, I think, is the distance and predicted magnitude. So here's the distance. You read up here. If it's here, you can say this region, it's here. You can see the eccentric below the domain here. It comes to perihelion down here in the southern hemisphere, southern galactic planes. It's there. I think if it were that close, as close as 300 AU down here, there are gravitational signatures that we've looked for based on perturbation of the spacecraft. And I think we would have seen them if it was that close. So I don't think it's there. I think it's up here in this high probability region here. So 400 AU, 500, 600, somewhere up in here. But the fun thing is to look at the magnitude. Even if it's at the far end here, it can be as bright as like 20th magnitude. Pretty cool. Anybody have a telescope in the backyard that can see 20th magnitude? I mean, often I ask this question, the answer is yes. You guys don't. You guys all live in San Diego. That's a bad place for your backyard telescope. But if you are somewhere, if you're giving this talk to amateur astronomers in a dark spot, they all answer yes. They can see 20th magnitude. No one's found it so far. So what do we do? If given this, that it might be anywhere from 20th magnitude to 24th, even 25th up here, the easiest thing to do is to go for low-hanging fruit. What if it is 20th magnitude? Go find a survey that you can do the whole sky to 20th magnitude. So we repurposed the ZTF survey out of, again, the Palomar 48-inch and looked for it. And the nice thing about ZTF is it looks at the sky night after night after night after night after night. There's so many observations of every spot in the sky in the northern hemisphere that I don't care if you're in the galactic plane. If you're in the galactic plane and behind a star today, you end tomorrow and the next day, and the next day, you won't be the next day. And then you are on the next day, the next day, the next day. We just have to develop techniques where we could basically connect the dots from arbitrarily spaced observations, transient observation. It just shows up as a transient one night only, right here, and gone. And we took all of the billion of those from ZTF and figured out ways to efficiently try to fit orbits to every single one of those. And didn't find any of those. We actually refound a lot of the Kuiper Belt objects that we found before, which is always irritating. There it is, my favorite picture. This picture is on the wall at Palomar. I'm going to steal it someday. If it ever goes missing, I stole it. So we have what we call our reference population. We took that whole MCMC model and we extracted 100,000 objects from it. So this is our reference population, statistically distributed across the sky of phrases and where they are. So it's the same plot as you saw before, just not quite as densely populated. So then we can say we embed this entire reference population into the ZTF survey and figure out what it would have found. And it would have done great. It found, everything up to 20th magnitude in basically the northern hemisphere. You see it out there. It's then to the southern. So I think this part we simply here. And we didn't find it. I'm going to quickly go through the other ones we did. Who else? Dark energy survey. Dark energy survey, because this is our reference population. It covers a little bit. It's not great, but, might as well look. And it didn't find it. It ate out that little region right through there. Next survey is not in Subaru, which you should have done, but it's with Pan-STARRS. We'll be here on Haleakala. Pan-STARRS, oh my God. What a garbage data set. I mean, it's usable data. Like, holy cow, what garbage. They have a warning on your page that you go to at Space Telescope about the data and basically say, under no circumstances should you ever try to take single night detections and use them for anything. Like, consider that a challenge. So we did. So we found like a trillion, I don't remember the number, a trillion single night detections of garbage, and a Keplerian filter is a really powerful filter. If you have enough clever algorithms to do it, you can take those trillion randomly spaced points and find any of them that fit. And we would have required 8 detections over the 5-year period. We just did it empirically. If we only required 7, we were still overwhelmed with garbage. If we went up to 8, we had no false positives or true positives. So there, pan stars, blah blah blah. So final one is actually Subaru. So Constantine and I, Constantine, you can tell he's a theorist. He's using oxygen on Mauna Kea. Clearly it appears. Subaru was good, not great. It was getting enough time on Subaru was just too hard. We did it through the tech exchange program, and they didn't want to trade very much. And so we never really got a good survey going on. So we wanted to do this region up to here, where in through the galactic plane. And in the end, it didn't really turn out so well. Even after we'd covered a region of the sky, we were only about 75% efficient to say that we would have found it or not when we looked at our embedded things. And that's, 25% that you look there and you missed it is garbage. So we're stuck. So we are stuck, but if you gave me, I'm a little over. Okay. If you gave me $1 billion, I'd be happy. And you said, give me $1 billion and say, build a telescope to go find Planet 9. I would build Viru. That's like, somebody did this for me. I don't know why they did this for me, but I would build that telescope. I would build all the infrastructure to look for transients and report them every single night. And I would find it that way. If Planet 9 is within our predicted range of parameters, and I can tell you why it might not be, and all the caveats to that if you ask. But if Planet 9 is there in that range of parameters, Vera Rubin has something like a 90% chance of finding it. I mean, it's perfect. It's going to cover the sky night after night after night. It has that same thing that ZTF does, where I don't care if tonight it's behind a star, or if tonight it was between a CCD gap, or if tonight it was cloudy. It will be there eventually. And to find Planet 9, we need, I'm going to say, 3 good detections from Vera Rubin. If you gave me 3 good detections, that statement is all based on not yet knowing how much garbage they will have in their alert stream. Like if they have as much garbage as Pan-STARRS does, and they might for the first year, you just don't quite know until you really start to see it. But if they have a pretty clear, good alert stream, 3 detections, you then go off to the telescope again to check yourself a 4th night, and that's it. Orbital mechanics is good enough. You found Planet 9. That's it. And so when might that happen? Based on those probabilities, that it's most likely right here. Right here, do you know when right here is overhead in the sky? Right now. That's right now. That's tonight. That's right here. That's like across Orion, the top of Orion, where the galactic plane is. If Vera Rubin is producing good data by this time next year, and if it's within our area, we'll find it. We'll find it by now. It will be found. And when we find it, I will tell you now, if we are the ones who find it, other people are looking. It's the data. It's Vera Rubin data. I mean, fantastic. If somebody else finds it before us, I'll be very happy for them, and then I'll punch them on the night. That'll still be happy. But if we find it, we will announce it immediately. There's no need to sit around and wait for some dumb Nature paper or something. We're going to actually publish it in the research notes, the AAX. That seems like the perfect vehicle for Planet 9, doesn't it? For y'all. So that's what I find. So read your research notes. Don't look on archive because they don't publish them there. It's stupid. Anyway, and that's it. I just want to end with the slide that we started at the beginning. There were some questions where this came from. How many people recognize this poster at all? Youth of America. So the movie Plan 9 from Outer Space. It was 1959. Directed by Ed Wood. Okay, if you want to knows by Plan 9 from Outer Space is a famous movie.
It's not on TikTok, but it's really bad.
It is not just really bad.
It's the worst movie.
It was voted by some directors guild as the worst movie ever. Literally true. I think you can find it on Wikipedia, and you can actually attempt to watch it. You will fail. You're like, oh, this is going to be fun. We're going to watch the worst movie ever made. No, it includes Vampira. It includes the last footage of Bela Lugosi, who died before it produced. Constantine's in it, interestingly enough. And so we saw their poster. But more importantly, 1959, Ed Wood is sort of thought of as a twisted genius. 1959, there's this scene where he's they're digging the graves and to get the zombies who are alien. I don't even know. But this, if you zoom in on this, 1959, Ed Wood knew what was going on. Look at this, 1959. You already know. All right, he thought there was something fishy going. Anyway, thank you for listening to my ridiculous